Good morning students, I welcome all of you for your online class. Myself Dr. T. Sudarshan Ram Perumal, Associate Professor EC Department. I am going to handle EC 8553 Discrete Time Signal Processing for you in this semester. Now we see the overview of the today's section. Today I am going to discuss the objective of the subject, outcome of the subject, what is the syllabus for your first unit, and review of the signals and systems, concepts of frequency in discrete time signals, summary of analysis and synthesis equations for fast Fourier transform and discrete time Fourier transform, basic signal representations, and introduction to discrete Fourier transform. So the objective of the subject means what is our motive or aim of to studying the papers. So in this paper we are going to study the 5 different units. In 5 different units we study 5 different topics. So in the first unit we are going to study to learn the discrete Fourier transform and their properties and the applications of linear filtering. So after studying your first unit you can able to understand the concepts of discrete Fourier transforms and their properties. And in the second unit, to understand the characteristics of digital filters, design digital filters in infinite impulse response method and finite impulse response filters, and apply these filters to filter undesirable signals in various frequency bands. So in the second unit we are going to study about the filters design in infinite impulse response and finite impulse response. In third unit we are going to study about the effects of finite precision representation of digital signals. Finite precision representation of digital signals we study in the third unit, and move on the fourth unit to understand the fundamental concepts of multi-rate signal processing and its application. So in the fourth unit we study the multi-rate signal processing and its application, and last unit we are going to study the concept of adaptive filters and its applications for your in the communication engineering. This is the outcome of the subject. After studying all the 5 units, at the end of the semester you can able to apply the DFT concept for analysis of digital signals and systems, and we can able to design IIF and FIR filters, and you can able to characterize the effects of finite representation of digital filters and design multi-rate filters, also apply adaptive filters approximately in communication systems. So these are the outcome of the subject. We can able to do all the things after studying the 5 units. This is your first unit syllabus. In your first unit syllabus we are going to see the first topic is review of signals and systems. Here we discuss the signals, what are the different types of signals and what are the different types of systems, and then we move on the concepts of frequency in discrete time signals, how the frequency will be represented in discrete time signals, and then move on the summary of analysis and synthesis equation for Fourier transform on discrete time Fourier transform. So we studied 2 formulas for each Fourier transform and discrete time Fourier transform, and then we study about the frequency domain sampling. We all are already study about the sampling theorems. So then we study about the discrete Fourier transform DFT and derive DFT from DTFT and properties of DFT. Then we study about the periodicity, symmetry, circular convolution, linear filtering using DFT, and then we study about the filtering long data sequence. So filters the long data information using overlap save or overlap add method, and fast computation of DFT using radix 2 decimation in time fast Fourier transform. We simply say that FFT, or in decimation in frequency fast Fourier transform, linear filtering using FFT. This is your prescribed books for your syllabus. First one is textbook and remaining 4 are reference book. the first book itself enough for studying the whole 5 units topics. It's a very easy and simplest book to study. Your first topic in the first unit is review of signals and system. So in review of signals and system, we are going to see the short introduction about your signals and systems. So first one is signal. So signal is nothing but it's a defined signal is defined as any physical quantity that varies with time, space or any other independent variable. So signal is defined as any physical quantity that varies with time, space or frequency or anything else of the independent variables. Types of signals means continuous time signals and discrete time signals. We use two different types of signals. One is continuous in time, another one is discrete in time. So continuous in time signal. So this we simply say represents CT. So continuous time signals are continuously varied in accordance with time. So the signals are continuously varied. The amplitude value is continuously varied according with the time. The continuous time signals are continuous in amplitude and time. These signals will be continuously present in the two domain, amplitude and time. They are denoted as x of t. So in continuous signals they represent x of t. Examples of continuous time signals is sine wave, cosine wave, triangular, etc. Next is discrete time signal, we simply written as dt. Discrete time signals is defined as a discrete instant of time or known as discrete time signal. The signal is present in the discrete interval of time, not in the continuous interval of time. So the discrete time signals are continuous in amplitude and discrete in time. The amplitude value is continuously changing, continuously varying, and the time is discrete in nature. They are denoted as x of n. So clearly remember, the continuous signals are denoted by x of t and discrete time signals are denoted by x of n. There t, here n. We must know that how the continuous signals will be represented and how the discrete signals will be represented. X of t means the signal is continuous, x of n means the signal is discrete. The example of discrete time signal is, the best example is the electrical signal is derived in the proportional with the physical quantities such as temperature, pressure, sound, etc. So in every day we have the temperature value from morning 5 to evening 5 o'clock. So in between this time period we have the infinite number of values, but we take only some of the sample value for identify the temperature level of the particular day. So this is the best example of the discrete time signals. Next we move on systems. So system is defined as a physical device. A system is a device that generates a response, that produces some output or generates a response based on the given input. Any system with produce some output with respect to given input means then we say that it's a system. So types of system, we have two different types of system, continuous time system and discrete time system. In continuous time system, the input is continuous in time. For in discrete time system, the input is discrete in time. Next we move on the concept of frequency in discrete time signals. In continuous time signals, we represent x of t is equal to a cos omega t plus pi. Pi is a phase shift, t is varies from minus infinity to plus infinity. In discrete time signals, x of t is replaced by x of nt. So n is the instant time duration for n is equal to 0 or n is equal to 1 second, n is equal to 2 seconds, n is equal to 3 seconds, like this. So your equation will be changing, x of nt is equal to a cos omega t is replaced by nt. Continuous time will be replaced by the discrete time signals plus the phase angle pi. Here the n is varies from minus infinity to plus infinity. Here also the omega value is 2 pi f. Next topic is analysis and synthesis equations for Fourier transform, discrete time Fourier transform. So Fourier transform, ft is nothing but Fourier transform, dt ft is discrete time Fourier transform. So what is the actual use of this Fourier transform. So Fourier transform is a bridge from time domain to frequency domain. You can change the time domain values to frequency domain values. The input is in time domain, then we can going to change this input time domain values to the frequency domain value. It's very necessity to for calculate our signal values. So Fourier transform is very much useful to convert the time domain to the frequency domain. Discrete time Fourier transform and Fourier transform are arbitrary sequence. That means arbitrary sequence is nothing but changing the sequence values at any time, whereas discrete Fourier transform can apply only to finite length of sequence. So DTFT and FFT inputs will be changing at any time, and it will be handle this type of changing input values, whereas DFT can apply only for the finite length of input sequence only. Next we move on analysis and synthesis equation for Fourier transform and discrete time Fourier transform. First we are going to see about the Fourier transform analysis equation. The Fourier analysis equation for a signal x of t is defined as x of s. That means the input is in time domain x of t, and we are going to calculate the signal value in frequency domain x of f. F is the frequency domain. So x of f is equal to integral minus infinity to infinity x of t e power minus j 2 pi ft into dt. So the Fourier transform will now changing the input value in the time domain to the frequency domain. X of f is equal to integral minus infinity to infinity x of t into e power minus j 2 pi ft into dt. When t is indexed into time with units of seconds, then f is indexed to frequency with units of cycles per seconds. We simply say that hertz. Now we see the Fourier transform synthesis equation. The Fourier synthesis equation for the signal x of f is defined as f of, if we know that frequency domain value, it can able to change the frequency domain value into time domain also. X of t is equal to integral minus infinity to infinity x of f e power j 2 pi ft into df. There we have j power e power minus j 2 pi ft. Here we have e power j 2 pi ft into df. Next we move on the discrete time Fourier transform analysis equation. The discrete time Fourier transform is a transformation that signal x of n into the complex valued function of the real variable omega. Here also we convert this discrete time value x of n to the frequency domain x of omega. The formula is x of omega is equal to summation n is equal to minus infinity to plus infinity x of n e power minus j omega n, where omega is represented as the real values. Next we move on the discrete time Fourier transform synthesis equations. The discrete time Fourier transform synthesis equation for signal x of omega is defined as the x of omega is the frequency domain. Now we can able to change this into instant time value. Therefore x of n is equal to 1 pi 2 pi integral minus pi 2 pi x of omega e power j omega n d omega. Now we are going to see about some basic signal representations. In discrete time signal processing, we use some different types of signal representations. First one is unit step sequence, second one is unit impulse sequence, third one is ramp sequence, and fourth one is exponential sequence. The above four signals will be represented in the continuous form as well as the discrete form. These four signals will be very much useful in your discrete time signal processing. We all should know clearly about these four different types of sequence. And first one is unit step sequence, or we say that unit step function. The unit step function will be represented in the continuous sequence format and also the discrete time sequence format. For continuous time sequence, unit step function is denoted by u of t. So continuous we represent u of t. For discrete we represent u of n. So here is a continuous time. So we represent u of t. So the equation is u of t is equal to 1 for t is greater than or equal to 0. 0 when t is less than 0. The u of t is present when t's value is 0 or greater. 0 or 5 or anything else, the value is 1. The u of t is 0 when t is less than 0, that means minus 1, minus 2, minus 3 up to minus infinity, the u of t value is 0. So please remember this equation is very much helpful for your further problem solving. Next one is unit step functions in discrete sequence. So the unit step function is denoted by u of n. There we can represent u of t, here you can represent u of n. So clearly understand, t will be used to represent continuous signal, n will be used to represent the discrete signal. So u of n is equal to 1 for n is greater than or equal to 0, 0 for n is less than 0. So n value is 1 continuously when n is greater than 0, u of n value is 0 for n value is less than 0. So next we are going to see about the second basic signal representation, unit impulse function. So this also represented in continuous sequence format and discrete sequence format. For continuous sequence, impulse function is denoted by del of t, is spelled by del of t. So t is continuous. Del of t is equal to 1 for t is equal to 0, 0 when t is not equal to 0. So del of t is enabled only t is equal to 0. So t oda value 0 irundha mattumdhaan del of t is equal to 1. Remaining value, all the values t is not equal to 0, t is not equal to 0, all the remaining t's values, the del of t is equal to 0. Unit impulse function for discrete time sequence, unit impulse function is denoted by del of n. Del of n is equal to 1 for n is equal to 0, 0 for n is not equal to 0. Here also the del of n is equal to 1 for the n is equal to 0 instant only. All the remaining instants, the del of n value is 0. Next we go and move on ramp signal. So in ramp signal it is represented by r of t. So t is represent the continuous signals. R of t is equal to t when t is greater than or equal to 0. So t is equal to 0 means RAM R of t is equal to 0, t is equal to 1 means R of t is equal to 1, t is equal to 2 means R of 2 is equal to 2, t is equal to 3 means R of 3 is equal to 3, like this the RAM signal represented. When R of t is equal to 0, when t is less than 0. In the negative values, R of t is 0 only. For discrete sequence, the RAM signal is represented by R of n. R of n is equal to n for n is greater than or equal to 0 and 0 for n is less than 0. So if n is equal to 0 means R of 0 is equal to 0, R of 1, if n is 1 means R of 1 is equal to 1, if n is 2 means R of 2 is equal to 2, like this these signals will be represented. For all the negative values of n, the R of n is equal to 0. Next we move on the exponential signal. The exponential signal will be represented by denoted by g of t or a of t, x of t, anything like this. So g of t is equal to a into e power b t, where a is greater than 0. The time signals will be continuously present in all the time instants. In discrete time sequence, the exponential signal is denoted by g of n. The g of n is equal to a into e power b n. The signals will be continuously present in the discrete time instant. That means t n is equal to 0, n is equal to 1, n is equal to 2, like this the signals will be continuously presented through the discrete time instant. Next we move on discrete Fourier transform, DFT. The discrete Fourier transform converts the finite sequence of equally spaced sample, that is a finite sample. I already told that DFT is working in the finite sample sequence. So equally spaced samples of function into a same length sequence of equally spaced signals of discrete time Fourier transform. So DFT is used to convert these signals in the time domain to frequency domain only for the finite length sequence. And DFT is said to be frequency domain representation of the original input sequence. The input sequence is in time domain, means it will be converted into the frequency domain by using this DFT formulas. DFT pair equation, that means finding DFT and finding the inverse discrete Fourier transform. So DFT means the input signal is x of n, time domain. We are going to calculate x of k. x of k is equal to summation n is equal to 0 to n minus 1 x of n e power minus j 2 pi n k divided by capital N, where k varies from 0 to n minus 1. In discrete time Fourier transform, x of k is given, we are going to find x of n. So x of n is equal to 1 by capital N summation k is equal to 0 to n minus 1 x of k e power plus j 2 pi n k divided by n. Your n, small n varies from 0 to n minus 1. For DFT we are using e power minus j 2 pi n k divided by capital N. For IDFT we use e power plus j 2 pi n k divided by capital N. Now we move on the example problems. Find the value of below signals. X of n is equal to 5u of minus n plus 2u of n plus 6u of n plus 1. They doesn't give any interval values, only they given the signals are in discrete in time. So according to this we are going to calculate the value for the first signal value and the second signal value. Second signal equation is x of n is equal to 2 del of n plus 3u of n plus 3.